Hey guys, I will be showing you guys how to do vector sum on the GPU. So I'll start with why the GPU. So like when we write normal code, the code executes sequentially. So let me get my brush here. So the code will always do operations. So let's say it's adding something, it'll do it sequentially instead of this is how code is all written. It'll all do it sequentially in normal cases. But on the GPU, all of this can be done in parallel. So let's say we are adding two numbers, 1 plus 1, and here we're adding 2 plus 1. Instead of adding it one by one, we can do it simultaneously and get the results back at a normal rate. So as you can see, doing it on the GPU can improve performance tremendously. It's good for optimization, and when you have like a lot of operations that you have to do, so for example in machine learning, linear algebra, or game engines, there's like a lot of calculations running in the background. So when you can do those calculations in parallel, you improve performance by a ton. So that's why GPU programming is really important. Vector sum in GPU programming is like kind of like the hello world to GPU programming, I would say. And I'm gonna assume that like everyone watching the video are absolute beginners in GPU programming, and but I do expect some of you to, expect you to know how to write basic C and C++ and pointers, memory, all that stuff. If you don't really understand memory allocation or pointers or C or C++, I would suggest just like poking around with the code, just like following along with what I do, and then just poking around and figuring out what each line does. I suggest doing that instead if you don't want to learn C or C++ from scratch. So before we start, I will start with a precursor on vectors, what vector sum really is. So you don't have to be a math person. So vectors are like just basically two arrays where you add the corresponding elements simultaneously. So what is a vector? So let's just say it's an array of elements. So 1, 2, 3. So this is a vector of 3 elements. And let's say there's another vector. I'll just call it 3, 2, and 1. So we have two vectors here. Both are just an array of elements. And when you do a vector sum, you basically add the corresponding elements. So this would be 1 plus 3, which is 5. This is 2 plus 2, which is 4. And this is 3 plus 1, so which is just 4. Okay, this is not 5. I can't add, so it's just 4. Yeah, anyways, that's basically how you do vector sum. So with that out of the way, I'm just going to get into some key terms that you have to know before you get into the code. So in GPU programming, there are two terms that come up a lot, which is device and the host. So host is where, host is basically your the CPU, or where your main code runs. So this is where all normal code runs, and the device is basically your GPU or graphics card. So this would be your I can't write, so it would be your GPU. This is where our code will run, and with this out of the way, you also have to know a few things about blocks and threads. So how does programming in parallel really work? So I showed you before that you have a bunch of operations or add operations that you want to do. So 1 plus 1 or 2 plus 1. So this is going to run in parallel, but we have to define the operation as a function. So basically, how would the graphics card know that it has to run the operation? So to define that, you basically define a function, just like in normal programming. So you will define a function. Let's say add. That function would add 2 parameters and return the and the third one. So third one would be the result. So if you give 3 parameters, it would add the 2 parameters and give the result. So in GPU programming, you can't really return the result in the function. They are always void. So instead of returning result, you have to pass a parameter and get the memory back from the GPU. You have to copy the memory back from the GPU. So this is like a core concept that you have to know. And finally, when executing in parallel, there are something called threads and blocks. So right now, when code is running in parallel, when operations are running in parallel, you can imagine it has blocks where different operations happen in different blocks, and once they're done, they come together for the result. But it's not that simple because our GPU has like thousands and thousands of cores. So each block has like a bunch of threads where our function can be run. So our function can be run like if our block has like 100 threads in it, our function can be run 100 times in the block. So that would apply for the blocks too. So when you're running in parallel, you could either run it in the threads in like each block. So if you're running like 10 operations, you can run it in 10 threads in like one block, or you could do it in 10 blocks with 1 thread each. So that is also something about parallel programming. And I'll get to the actual problem of vector sum and what we're going to do now. So vector sum, like I told you before, you have two array of elements and you just add the corresponding element. That's basically what vector sum is. So when we have what vector sum is, so how we're going to do this exactly? So I will paste some code. This is I will code the GPU code myself. This is just like normal C where we do the same thing on the CPU. We're not doing it in parallel, we're just doing it normally. So I will just go over how we do it here. So we have we initialize three arrays. So A and B are our input arrays, and C is our resulting array. So with the loop, we just initialize our A and B values. So we just have it as 1 to 10 because we have 10 elements, which is 1 to 10, and we call the add function. In the add function, what we basically do is we iterate through the third array, and for each element we just add the corresponding A and B. So that's basically what we're doing. And once we have that, we just display the results with like a loop. So that's basically all we do in the CPU. This is pretty simple, and I will show you how to, instead of iterating with like a loop here in the function, I will show you guys how to do it in parallel in like a function, or in a function in the GPU, or the kernel. It's not really called the function in the GPU, it's called a kernel exactly. Yeah, that's pretty much all I wanted to talk about. I'll get to the code. You guys can code with me, or just look at how I code it, and that's pretty much it. I will be showing you guys how to code the kernel here. So I'll just open my editor. Yeah, I'll just start over. So first we have to include our header file. Yeah, we have to include our header file, and we have to define our global variable. So I'll just define it as 10. So this is going to be the length of each of our vectors. So after we have this, we'll define the main function. So this is all stuff in C and C++, all written 0. And once we have this, we finally can start on the code. So at the start, we had to define 3 arrays for adding our for vectors. So that would be A with length n, B, and C. After we have this, this will be for the host. We have to define it for our device or our GPU. So that would be, we have to define some more. So that would be a bunch of pointers. So I'll just call this device A, device B, and device C. Once we have this, we'll have to allocate memory. So we want our GPU to allocate memory to here, so that it could perform whatever operations it has to do. So we'll allocate memory for this with something similar to normal C and C++, CUDA malloc, or memory allocation. So then we'll assign a void pointer to device A, and we define the size of it. So we want it to be we want 10 integers to be vector. So this is how we define the size for it, and I'll just allocate it for all 3 of our arrays in our device. So that will be just like this. And once we have this, I'll just define the logic for freeing the memory once we are done. Just in case I don't forget, I usually forget about this, so I usually do this before I write any logic. So just copy paste it. Once we have allocation and freeing the memory, next we have to define the function. We basically have a function that will add like the individual element in the vectors correspondingly. So to do that, we'll first declare the kernel with global and void. All kernel has to return void, and we'll just call this add, and these are the parameters. So that would be, once we add this, we have to get the ID to add the corresponding elements. So how would we get this? It depends on how we're going to do it exactly. So I will do this on blocks. So we're going to do it with 10 blocks first, and 1 thread per block. And after that, I will show you how to modify it so that it works for individual threads in like the same block too. So we'll first do it for blocks. So that would be block ID x, yeah, and x, and if ID is lesser than our maximum variable, our maximum count, we'll add it. So we'll add it based on ID. So this is pretty simple. Yeah, so we have our kernel function that we're going to call in our main function. But before we're going to do this, we have to get our we have to set the values for our A and B arrays. We have to prepare it. So we can do that in the function itself, but I'm just going to do it in the CPU just to show you how to get data from the CPU to the device or GPU. So I'll just define a simple for loop. So 0, and the main condition is it should be lesser than en, and it'll increment, and finally we just add. So if I will, you just have it as I for the final results to be simple. For now, you just have it as I. And once we have the entire array for A and B, we have to copy this into the device so that it can perform the calculations on it. So to copy this array to our device memory, we will use a function called CUDA mem copy. And once we have that, I think I messed it up. Yeah. Let me look at it. I don't remember the syntax and my IntelliSense is not working. So yeah, I'll just copy this just in case. And yeah, anyways, yeah, so we have the mem copy. So first we have for the parameter, so we have to define where we are going to copy to. So the first parameter will be our target. So where we're going to target, we're going to copy the memory. So we will be copying it to device A, and we will be copying it from the array A, and then we have to define the size of the copy. So it will just be like before, and we have to just define the flag for the direction of the copy. So I'll just get the direction of the copy. I don't remember the exact syntax, capitalization, and all that stuff, so I don't really want to type it out myself. And you basically specify the direction of the memory copy. So you basically say that like it goes from the CPU to device, basically the CPU to GPU, or host to device. The host is basically the CPU. I think I said it before. And just like that, we do it for for the B array too. So we have to do it for the B array as well. So I'll just copy paste this and rewrite it. So we got our A and B arrays in our GPU, and we can use it in our function now. So now all we have to do is call our function. So let's call add, and we'll pass the parameters like usual. So we'll just do this. It's just like a simple function call, but unlike simple function calls, we have to define the number of blocks and threads we're going to use. So here we are using 10 blocks and one thread because we're using blocks as the ID. So you're going to use 10 blocks, so 10 individual blocks will be running our function or kernel, and there will be one thread running the execution or running the function per block. So once we do this, we have to so first we have done the calculations by just calling this function, but we have to print the results, right? So to print the results, our C array is still null. It doesn't know what's there in device C or anything like that. So we have to copy the results from our GPU back to host. So we'll just reuse this similarly, but I'll just write it out. So we'll just come and copy and device C. I'm sorry. So the target is C. So we're gonna get it for the C array, and we're gonna get it from device C, and here of the sizes of vector 10. And for the flag, I'll just copy this, but we have to change the direction. It won't work exactly. We'll just call device to the host, and yeah, that's it. And we basically define the direction as we're gonna get it from the GPU back to the CPU for C. And once we have this, we just have to print the results. We have everything that we need. We have done the calculations. We just have to print the final results. So I'll just reuse the for loop again, this time to print the results. So I'll just use printf, and I'll just define a flag. So and once we have this, we have to define it by I. So we just B and C. Yeah. So yeah, that should be it, I think. Let's see. Let's hope it runs. So you can run it with the nvcc command, and I'm specifying the binary file to output, and finally I'm just going to specify the architecture for my GPU. It strangely needs that, but I don't think you might need it. It might be different for you, but I don't think you would need it. It compiled, and we're going to run the final file. As you can see that we did the calculations, all of it in parallel, and we're outputting the results. But before we go, we did the calculations all on our blocks. So blocks are basically, as I said before, each thread is what executes a function, and each block has like multiple threads. So when we're calling the function, we're just calling it for 10 different blocks, but with only one single execution in that block. So it only has one thread, so each block can have multiple threads. So we could instead of calling it all in 10 different blocks, we could instead just call it in one block, and in that block we can call it in 10 threads. So this will also run parallelly and concurrently, but we just have to change this so it will use this to thread ID instead of block ID, because we're not using block ID anymore. So it should still compile and work the same. So let's just output the binary file, and I will run it. I think that should be it. If you have any questions, just comment, or you can message me, I guess.